All right, and so now we are ready for the next example, where I call it example 2. But the idea of this entire example 2 is exactly the same with this. We're going to use the properties of logarithm to rewrite a given expression into one single logarithm. But we call that example 2. So a slightly more advanced class of problems right here. Okay. All right, so let's look at our first problem here. We're looking at now part A. So how about 3 natural log of x plus 2 natural log of y? Okay. All right, so before I start getting into tackling down this problem right here, let's look at let's look at the problem here and find out what's more advanced compared to the version we've done to those problems in example 1 earlier. Okay, so we still got multiple terms just like that, and then each one of these involves a log of the same base, a log of the same kind. So here is a natural log, and here is also a natural log, log base e, 2 terms with the added. Okay, so that's making it like the earlier problem. However, what's different here is that each one of these terms comes with a coefficient. All right, it has a coefficient. All right, so now coefficient rings a bell. That property number 6 that I introduced earlier now is going to start playing some role in this particular problem. So we're still going to have from 2 terms being added, we're still going to combine them using the product to sum rule. But then on top of that, we're also going to blend and combine together with that rule, that property number 6 that we've learned about, the rule that we brought a power of a base down to as a coefficient in front, or we can go the other way around. All right, so now allow me to introduce the standard step-by-step work in this problem right here. So first of all, on each term I see there's a coefficient, like say for example in this first term I see that coefficient 3. And then in the next term I also see another coefficient. And sometimes, each term have sometimes some terms has a coefficient, and then some other term has no special coefficient other than just a 1. So here each term has its own coefficient already. So now the first step is indeed to take care of all the coefficients. Okay, so I repeat, the first step is to take care of all the coefficients on each term. So the first term here has a 3 times a natural log. So here I'm going to apply immediately that property number 6 that we have learned earlier. So that will become, that's making it, the first term here is making it to become natural log, but now the 3 is being brought back inside the log to become the power. So now it's natural log of x cubed. All right, so this is how I use that property number 6 that we've learned earlier. And then still it's adding. So like I said, primarily at this point our goal is to handle each coefficient in front of, or the coefficient in front of each of our terms here. Okay, so moving on to the next term. And by the way, we're done with taking care of the coefficient of the first term. So now for the next term right here, the coefficient is 2. It's a coefficient other than 1. Okay, it's not like any of the problems we've done in example 2, in example 1 earlier did not have a coefficient. They all have a coefficient, but all of those problems we did in example 1 had a coefficient 1. But now we're starting to run into, or we're starting to face with those problems where each term has a coefficient other than 1. All right, and that's where things start creating some more work for us here, or become a little more advanced. So now that term here, back to this term right here. And when it comes to these terms where we handle the coefficient, and really which one first and which one last should not really matter. But again, we want to work from the left to the right. So whichever term on the further left, it's the one to be handled first, and then sequentially we're moving down the list right here to the right hand side. So now on the next term on the right here, I'm looking at 2 times natural log of y. Okay, so now once again I'm going to use that rule, or that property number 6. I'm going to bring that coefficient inside the log, bring the coefficient inside the log. And earlier, that's what I did here. I brought that coefficient inside the logarithm. So now, how would that coefficient go inside the log to become? So it's now natural log. So once we bring that coefficient inside the log, it's no longer there, or it just now remains with the coefficient 1. But now inside the log, we have a y to the power 2. All right, and this is, I'm going just really side by side and as closely as I can with that rule number 6, with that property number 6 we have learned earlier. Okay, and so now at this point right here, we brought ourselves back to that to a problem similar to those problems we've done already in example 1, where we have simply just 2 logarithm terms, where each one of these has just a coefficient 1. And then it's now adding. So now I can start using that sum to product rule, okay, or that property number 4 to bring these 2 terms, 2 log terms of the same kind into 1 term. All right, so now the next step here, so that was first step, taking care of the first of all the coefficients to make them to become the powers inside the log. And now the next step now is once we are done with all the coefficients, now we can combine them together. So now this is now 1 log term. And now, just like we've learned back in rule number 4 right there, or property number 4, and now these 2 will come together as a product. So now x cubed times y squared. And that's how I'm done. And really at this point, x cubed times y squared can no longer be simplified. We're done with our problem. All right, and so as far as achieving our goal, the goal of the problem is to use the log properties. And see, we have to use multiple properties. Okay, in this case right here, 2 properties together. So first, we take care of all the coefficients, and then now we can combine all the log terms together into 1 term. But now as soon as we reach 1 single logarithm term, we know we're done. All right, so that's how I've done part A. Okay, and so now, this is what we need to be aware for the rest of the problems in example 2 right here. It's all about each term, each logarithm term has some kind of coefficient other than 1. Okay, and then from that point on, we are going to, so the first step, it looks like I really made you fall into that impression that, and it should be the way. We take care of all the coefficients first, turn them into the powers inside of each log. And then from there, now in the next step, ideally we should only have multiple terms or scattered terms, but only with coefficient 1. And then after that point, we can start combining them into 1 term, just like how we did in example 1 earlier. All right. So now we are ready for part B of our example. So let's look at the following problem. All right, so now minus natural log of x, okay, minus natural log of y. All right, there are many ways of seeing this problem, but at first sight, this problem at first sight seems simple. It looks simple, and then anyone learning from this lesson is starting to wonder, how come I didn't put this problem as one of the problems in example 1? But as a matter of fact, if once you're through with how I break it down, you're going to realize it deserves its place to be in example 2 right here. Okay? Because example 1 is where we simply just looking at coefficient 1. But here coefficient is not really all 1. Yes, that coefficient in front of this logarithm of y, natural log of y is 1. I agree. And there's a subtraction, there's a difference between these 2 terms. However, the way how we see this first leading term is a little trickier, where that's why I could not put this in example 1. I intentionally put example 1 to involve only those where the first term was completely positive with the coefficient 1, and then the rest is whatever coefficient 1, but it could be plus or it could be adding. Okay, so here's how I see it. That first term right here is the problematic one. Okay, I see this as a coefficient other than 1. I see this term here has a coefficient minus 1. Okay, this term right here in particular has a coefficient minus 1. This is the same as negative 1 times natural log of x negative 1 times natural log of x. Okay, pick up experience from right here and there throughout how I work through the problems like that. So in that case right here, I see the minus sign here as negative 1 coefficient times natural log of x. So now in that way, okay, so see negative 1 times natural log of x. That's how I'm seeing it. And so now that's after that quick little note right there. Now calculate it down. Now I have to use a rule number 6 here. Now I have to use the rule number 6 here, or property number 6 to handle this problem. Okay, so with this problem here, we're looking at first term to become natural log. And now I'm going to, as I said, first step now, once we have identified that we have coefficients other than 1 throughout our terms right here, then we're going to spend our first step right here taking care of all the coefficients first. Okay, so that coefficient here is negative 1. Now in my first step, really I'm going to turn that into natural log of x to the negative 1 power. Okay, and then now it's a subtraction sign right here. So subtraction, we did have a rule for difference to become a difference to become eventually a quotient inside a log. And so we don't necessarily have to see this as a coefficient negative 1, even though you can too if you would like to. But now I can see this simply just as now we have a 1 term and positive coefficient now. But 1 log term subtract another log term. That's how I'm seeing it. All right. So now in this case, now we can apply property number 5 or rule number 5 right here to turn from this difference to rewrite this difference of 2 logarithms of the same kind into 1 logarithm term like that. Okay, so now it's logarithm, according to what we've learned, logarithm of, or natural log precisely, of x to the negative 1 divided by y. All right, so as far as combining all multiple log terms into one single logarithm, we're done. But at this point, I'm not quite satisfied with the way how this answer is expressed right here. So due to the fact that there's a negative power inside of my log, I don't like that. So we're going to rewrite that as natural log. And so with some simple algebra we have learned from our previous course, we can rewrite this as we can bring this negative power of the x to the denominator and making that 1 over x y. All right, that's our final answer. Okay, that's our final answer. So, admittedly, this way of how I handled a problem was just simply my style. And now I can guarantee for anyone watching this, or guarantee is probably not the correct way, but now I can say this to anyone watching or learning from this lesson. My way of approaching this is not the only way. But the part I can guarantee is that no matter which way you approach, for this particular problem, there has to be at least once that you apply rule number 6. Rule number 6 is all about that rule where we bring the power, we bring the coefficient inside the log to make it a power. That rule right there. But at least once you have to go through that rule number 6. There's no way for this problem to simply just combine as usual, as just simply apply either rule number 5 or rule number 4. We have to at least at one step use rule number 6. Okay, so the same problem here. Let's not rush. Allow me to come up with one more solution. Same for this same problem, a slightly different approach to emphasize what I meant earlier, that I can guarantee that no matter which methods you approach for this problem, you have to go through, there has to be at least once that you apply that rule number 6 right there. Okay. Alright, so now for this part right here, it's supposedly scratch work, and I'm just trying to sketch out some direction, some thought. So somebody seeing minus log of x minus natural log of x minus natural log of y, somebody can approach as following. We can factor out a negative sign to turn that into natural log of x plus natural log of y. This is completely awesome. Nothing wrong with that solution. Okay? And then from the inside out, according to the order of operations, so here we're looking at handling the inside, the sum inside of the, well, because brackets in our understanding, it's just a written form in case we have more than one layers of parentheses, but it's just really brackets here, it's just parentheses. So according to order of operation, we have to work with what's inside parentheses first, and then there's what outside. So that means I'm going to keep the negative sign here, but the two log terms now, they are single, there are coefficient 1 on each one of these terms right here. So we can apply our, well, adding these two, we can apply that rule number 4 that we've learned earlier and turn that into 1 log. So natural log of x times y, by simply applying sum to product formula. But then we still got stuck with that minus sign. And so now once again the minus sign here can be seen as a coefficient negative 1 times natural log of xy. And this is where I was saying at least we have to run into rule number 6 to be applied once. And this is, I'm about to use rule number 6, even though the order of the work is slightly different. Okay, so now I'm going to bring that into natural log of x times y, okay, to the negative 1 power. All right, and then x times natural log of x times y in products to the negative 1 power is indeed, now that part that's still visible on the board here from my actual work earlier was 1 over xy, 1 over the product of xy. Isn't that the same as this right here? Natural log of, and now this xy in products to the negative 1 is the same as, isn't it the same as 1 over x times y, like that. And so again, we had to use rule number 6 right here. Okay, for that step here, there has to be at least one. Okay, and then the same problem, somebody else, same problem here, but as a different approach. Somebody else can think of that as a, okay, so applying rule number 6 right there. So natural log of x to the negative 1, and then somebody can see this also as a negative 1. So add with a negative 1. So now it's natural log of y to the negative 1. Because as I said, somebody can see this algebraically as negative 1 times natural log of x plus negative 1 times natural log of x. And so that student, if that person decided to go this route right here, then now we have two log terms with coefficient 1 right here added together as a sum. So now we can combine them into 1 log. So x to the negative 1 times x times y to the negative 1. But then now with our algebra, and this is where we had to apply rule number, we apply rule number 6 right here. So, but in this approach, we applied it twice, okay? And then 1 over x and over y. We all gonna come to the same final answer right there. But like I said, I can think of 3 different approaches right there, okay? But so my approach focus on term by term, but these are the more creative approach. But in any approach, you are gonna have to, for this particular problem, actually, and anyone going through this problem have to at least spend 1 step for the rule number 6 to be applied in. All right. All right, so now let's continue further on this particular problem. So let's look at part C of our example. All right, so part C here, I'm looking at, how about log base 10, a common log of x, okay, minus a 1/2 log of y, okay, and then plus 3 log of z, okay. But so allow me to agree with within my own, allow myself to be consistent with my own style right there. So even though one problem can have multiple approaches, okay, but now I already point out my own style, my own approaches that if I would do it personally, I'm gonna just take care of all of the coefficients on each one of these, and then except for the very first term, if we have to, in case it was a negative sign, but here it's already positive sign. Okay, but then anywhere here, whatever negative sign or plus sign, we are going to treat that as just either subtraction or addition. Okay, and so my point now is that the first term here, I see only a coefficient positive 1, so there's nothing need to be done here. In the next step, I write it the same. And my point is, the first step I'm going to lay down, for the first step, I'm going to lay down that foundation where we will simply just take care of each coefficient on each term. Okay, of the coefficient on each term. So now really it's a subtraction sign, but then this term has a coefficient 1/2. Okay, so 1/2 becomes, now when we bring the 1/2 coefficient inside the log, it becomes the log base 10 of y to the 1/2 power. Okay, so now be aware what 1/2 power means. It's a square root of y in here, if we have to think of it that way. But for now, at this point, it's not important. We have just now achieved our goal of bringing that coefficient aside from the operation sign right here, aside from that subtraction. We brought that coefficient inside the logarithm and made it a power, okay, an exponent. And now I'm going to add. And so now adding here, or here there's the subtracting, there's adding here, but in the end I want to focus on that coefficient. So that coefficient being 3, so now I'm going to bring that 3 inside a log. So that's first step for them in my style, and like I said, allow me to be consistent with myself here. So I set out that path that I chose. Okay, we take care of all, to keep things organized, we take care of all the coefficients first. Okay, and so we focus on the coefficient. So except for the first term, if it was a negative, then we're going to treat it as a negative power. Otherwise, we're only going to focus on just the positive part of that and then leave these signs as just either subtraction or addition. Okay, so we're only going to tackle down the positive part of the coefficient. And now that becomes a log base 10 of z, but z cubed. All right, so now one goal is now achieved right here. All coefficients now are coefficient 1, and these different signs here, they're just subtraction and addition, subtraction and addition. Okay, but other than that, all our entire goal has been achieved right there. We have brought all coefficients to become powers inside the log. All right. And so now in the next step, now we're going to go back and do it the way how we did in example 1. We're going to group 2 at a time from the left to the right. So the grouping the first 2 terms is now a subtraction. So it's a difference here, the difference between 2 single log terms. And so now I'm going to make that, I'm going to turn that into logarithm, a log base 10 of an x but over y to the 1/2. Okay, but at least I'm done with that term, combining these 2 terms into one logarithm. I now have a logarithm base 10 of a quotient. All right, and so once again, all it took here is to be aware, to pay attention on the order of subtraction among these 2 terms right there. Okay, so the logarithm log base 10 of x comes before the subtraction, comes in front of the minus signs right here. And so now I have to put that x on top. And then the y square, the y to the 1/2 power is at the denominator. And I'm going to add, and then we have log, okay, base 10 of z cubed. All right, log base 10 of z cubed. And now we are, at this point right here, we are down to only 2 terms. And then they are connected by the adding work right here. And they are connected by an addition like that. And so now at this point, the way things work, okay, it's just like how it is for example 1. So now I'm going to go ahead and combine these using the sum to product rule over here. And so now it becomes logarithm log base 10. Okay, and now it's going to be, I'm going to multiply the fraction here with that z cubed together. So it's producing x times z cubed divided by y to the 1/2. Okay, so that's one way we can express our final answer. Okay, so x z cubed over y to the 1/2 power. Okay, so that's one commonly accepted answer. And then, as I said earlier, this is already one commonly accepted answer. Log base 10 of x z cubed all over y squared. Y to the 1/2 power in the denominator. Okay. However, do watch out that some instructors out there, aside from me, may prefer his or her students to write the same expression here, but having the inside here completely free from fraction powers. So in that case, the same expression here, you can write it as a logarithm base 10 x z cubed, but then instead of writing a fraction power like this, some instructor may prefer to his or her students to write that as a root expression. Okay, that works too. So that's another way of writing it, and that was another way of writing it. All right, so I just point out different ways like that. All right, of how you can write the final answer, but any one of these two, they are already in simplified form. All right. And so now we are ready for part D of the example. So let's look at part D right here. So I have now 2 times log base 10 of z, okay? As a matter of fact, it should be of x plus, and now I have a 1/3 log base 10 of y minus log base 10 of z. All right, so these are 3 different terms of the same logs, log base 10, log base 10, and log base 10. Okay, and then now each one of these has some coefficient. Each one of these has coefficient. The last term has a coefficient 1, and then being subtracted from this middle term. But the middle term has a coefficient positive 1/3, and the first term has a coefficient positive 2. So these are the two terms having a coefficient other than 1. Okay, so in that way, once again, just to see how I'm consistent to my own style of doing it, my first goal is to handle all of the coefficients existing in front of each one of our term like that. Okay, so the first one right here, it's a positive term, but it has a coefficient other than 1. So now I'm going to bring that inside the log. So now from the left to the right, it's logarithm base 10 of x squared. That's what this first term immediately becomes in the next step after we took care of the coefficient in front of the term. So we take care of all of the coefficients first. So in this kind of work where we're trying to rewrite a lengthy expression into one logarithm, and a lengthy expression, I mean an expression that has multiple log terms like that. And when we're in that kind of work where we bring it all into one single logarithm, then if there are coefficients other than 1 involved, then the first step is to bring all coefficients inside the log as a power. Okay, and that's what I did. And so now it's adding, okay, it's the addition right here, and then now this coefficient here is positive 1/3. I'm going to bring it inside the log and making it log of logarithm base 10 of y to the 1/3 power. And you can also think of this. Be aware again, like I said in example in that part C earlier, some professor may prefer his or her students to write this 1/3 power as a cube root of y. Okay? If you're learning with me, I'm okay with either way. And then minus, and now it's you see we want to leave this, we want to understand that minus here as a subtraction, as an indication for subtraction. So really that coefficient here is coefficient 1. So in other words, nothing to worry about for the last term like that, for the third term. But now at least once we have arrived at this point, rule number 6 is done. We're done applying rule number 6. That's what I meant. But now we're just simply about to apply from the left to the right 2 terms at a time. From the left to the right 2 terms at a time. Then rule number 4 comes in first. And then whatever comes out of that, we're going to apply rule number 5. And rule number 4 and rule number 5 are similar. Okay? All right. So now I'm going to combine the first 2 terms here in as an addition. So it's a sum of 2 log terms now can be rewritten as a log base 10 of x squared times y to the 1/3. All right. So no one should be surprised about this anymore. Okay? Because I have just used rule number 4 here, or property number 4. And then don't forget we have a remaining term that's subtracted from this. So we have a difference between this term with that log base 10 of z, with that last term like that. And so now all of a sudden we realize after using rule number 4, we came down to only 2 terms. And now only 2 terms connected by the subtraction sign right here. All right, I'm ready to come up with the final answer. So now we can use a difference to quotient formula or rule or property. Okay, log base 10 of, so just when it comes to subtraction, we just simply need to pay attention to the order of the order of the subtraction. So x squared y to the 1/3 is inside the log term that comes that stays before the subtraction sign in front of the minus sign here. So in that way, now I'm going to write that as, I'm going to write the x squared times y to the 1/3 power on top, and then now we're dividing that by z. But at this point, we know that we are officially done. All right. So log base 10 of x squared y 1 cubed y to the 1/3 power all over that entire product over z. All right, and then again, some instructor may prefer so for a problem like that, where the answer was log base 10 of x squared y to the 1/3 over z, be aware that some instructors aside from me, other than me, may prefer his or her students. So anyone learning this lesson right here should be aware of what your professor is expecting. Okay, so some professors may expect the students to write this fraction power as a root. So now if we have x squared times a cube root in product with a cube root of y, and we're dividing that by 0 here, and then this is another completely acceptable answer right there. Simplified and acceptable. Okay, different choice. It's just a different choice of how we're writing the expression right there. All right, so that's part D of our example. So for this problem number 2 right here, there's no need to have an FYT right there. So let's now move on to example 3. Okay. All right, so here we are at example 3 right here. So let's look at, and let me spend some time writing down the worded instruction of example 3 right here. Let's use the properties again. Okay, we want to use the properties of logarithm, of course. So we use the properties of log to expand. So now this term right here, if it already caught your attention, you see earlier example 1 and example 2 is all about we had a very lengthy or expanded form of a problem, and we wrote it all at the end. We shrunk it down to only one logarithm expression, one single logarithm. But now we're expanding. Okay, so keep that word in mind right here, and I'll explain that a little more. So think about it. It's about we're about to go backward from a small logarithm expression. We are expanding it out bigger and bigger, more terms involved, and that's what expand means. Okay, so use the properties of logarithm or log to expand the given expression. Okay, the given expression. All right. We want to use the properties of log to expand a given expression. And so now, before I really get started into this problem, for the first couple of problems of this example 3 here, allow me to move really on slow pace right there so that I can explain. It starts getting a little when it goes the opposite way. Earlier in example 1 and 2, we just go from lengthy expression and we simplify it down to one single logarithm. So here we are about to go the opposite way. We are going to start out with one logarithm. We're going to expand it down into multiple terms having logs, but then allow me to explain in real small steps so that I want to reduce when you're on your own independently to work on these problems. You should be able to carry through. Okay, and so allow me to at least allow me to provide that opportunity to right here in the example to explain each of my steps of how I approach it. Okay, and then a lot of order of operations will be involved here. Okay, so now part A. How about we're just simply looking at a logarithm, and here let's look at and for simplicity, these rules work on any logarithm. It works on log base 2, log base 3, log base 10, and whatever, the natural log base e. So in that way, there's no reason that I'm going to hop in with a log base 2 or log base 5. They're all going to work the same. So to simplify, to reduce the amount of writing, I'm going to stick with either just log base 10 or natural log, okay, to keep life simple. And you have already seen that throughout the entire example 1 and 2 already. Okay. All right, so now we're having at start here a log base 10, a common log of x to the 7 times y to the 4th times z to the 5th. Okay, it's a product, and really writing these multiplication sign is just optional. Anyone viewing this lessons, you are at the pre-calculus level. You should be mature enough to see that x, 7, y, 4th, and z to the 5th power here, it's a product between them. Okay, so now allow me to just get directly in of how I do it step by step. But then once I'm done, I'm going to explain each step in details with my detailed reasoning. Okay, so that you can see why a step is done. A step must be done before the next step. Okay, so right here from this, for anyone who already understood why I did that, that's good. The later part of the explanation, you can fast forward a little bit. But in the way how I see this, it's a product between these powers. It's a product of powers. So I'm going to use property number 4, product. I'm going to break it down to sum. There's a product there. Okay, and then there's a product there. That's why I erased it earlier, but now I have to put it back in to make it real clear. Now we have a product. So we can write it down as log of x to the 7 plus log same base. And of course, the rule we had was just involving two terms, the factors in a product, and then broken down or expanded down or broken down to two terms. Okay, but we can extend that, and anyone viewing this lesson is at a pre-calculus level where your mathematical mind is already at a certain level of majority. Okay, so you can understand that we can extend that rule into 3 separate factors in a product. So we can break that down into 3 log rules. Okay, so simple enough. You can see that it's log base 10 of x to the 7 plus log base 10 of y to the 4th plus a log base 10 of z to the 5th. So that's the first thing so the first step here is indeed I use directly the products to sum rule and applied it here and broke it down into 3 separate terms. That's the first step, and allow me to keep moving on. And then I'm going to come back explaining why I do this step before the other steps, and then some other step before another step. I'm going to give all of those explanations. Okay, and so in the next step now, at least after breaking it down to 3 separate terms here, due to the fact that the beginning problem had 3 factors. Okay, then the next step now is that each one of these log terms, let's look inside of each of the logs here. Let's look at the inside argument of each of the logs here. We have a power, we have a power, and we have a power. And so now we're going to take care of the powers being the next step. So the power here, that rule number 6 now is going to apply. Okay, for the first term, it's log base 10 of x to the 7. Now I'm going to bring that 7 to the front to make it a coefficient, making it a coefficient. So now it's going to be 7 times log of x. And so now, right out from rule number 6 right here, then now that power inside the log becomes just simply power 1. Okay, but now we have a coefficient. So it's 7 times log of x, log base 10 of x. So, and then it's going to be addition. And then I'm going to move on. Now I know I'm done with first term. Now I'm moving on to the next term. Okay, and so the next term has y to the 4th. Okay. And so now I see a power. So with property number 6 we have learned earlier, I can bring that out front to make it a coefficient. So that power 4 now is made and is turned into a coefficient. And then 4 times log base 10 of y. So the power inside the logarithm now is only just 1. So this is where I call it, it's just a simple power 1, linear power. Okay, linear term inside of that. All right, let's take care of the last one right there. Okay, so now we're looking at that power can be turned into a coefficient in front of our last log term, and the power here the power inside the log can become just power 1. So now we're looking at plus 5 log of z. Okay, log base 10 of z. So as far as the final answer, we're done right here. We're done with that. Okay, so now we have the idea now is that each one of our terms contain only a simple log. And simple log, I mean a log, whatever base that is, of a one single number to power 1. A log of base 10, okay, that same base with whatever we started out. But it's a simple log in the sense that log base with the given base of that number to the power 1. So having the power 1 for that argument inside of the log. And then these coefficients came out due to the power that we've had involved from the previous step. All right, so as far as the steps and then getting to the answer, we're done here. We're done with this problem. But now allow me to explain a little more thoroughly why I did the breaking for a problem like this. Really, we're having a lot, right? At first sight, we have a lot to see. There's multiplications, there's products, well, and then there's raising powers here. We got a lot of things involved here. We got a lot of operations involved. So how do I know that I have to go breaking this as a product? How do I know I have to break it down? I have to see this as a product and break it down into the terms, the sums of the terms first, and then after that I use rule number 6 after. Okay, how do I know the order of the work here when it comes to the kind of problem where we expand from one single logarithm into multiple terms? Okay, so how do I know which steps must be done first and which steps must be done after? Okay, so here's my explanation. Okay, and I may not be able to guarantee that this is the best explanation right here, but I try my best here to explain. Okay, because I haven't seen it explained much anywhere throughout textbooks here. So this is probably too ultra basic, but it's worth your attention a little bit. So now, just think about the part inside of the log. So now we had that log base 10, okay? And then I have to write it real big right here. So x to the 7th power times y to the 4th, and then times z to the 5th. And so as I mentioned it out loud, there's quite a few different operations involved here. There's a multiplication. And then when it comes to multiplication, then we once it's all multiplication, then we're gonna go from the left to the right, 2 at a time. So that's easy to handle. So all multiplications have the same order, same priority. But now between multiplication and powers that's involved together in one problem, then we know according to PEMDAS. Okay, so PEMDAS is short. This is now becoming, it started out for the students within the United States right here, but now becoming quite international now. P stands for parentheses. And it's an order of operation. So parentheses, okay? And then the E here stands for exponents. Okay, that means these things right here. Okay, and then M and D, they really are, we write M before D, but really they are about same priority, same precedency. Okay, so multiplication or division comes after exponents. Okay, this is multiplication or slash division. All right, and then after that, the last one is addition or subtraction. Okay, so now, why do I mention order of operations here, or for short, PEMDAS? So according to the way how it is that we've been introduced to this PEMDAS ever since our first day introduced to math. Okay, that means anything being inside the parentheses, we have to take care of that first. And that's why now if we count this as an operation and inside of the parentheses here, we take care of that first. But see, let's not worry about the log because if there's a log, we do these kind of problems. So let's just focus right inside the parentheses. inside of the parentheses is at least what's existing inside parentheses is here is there's product and there's exponents, multiplications and exponents. So if we were doing a calculation, I said again, if we were doing an evaluation problem, a calculation problem, then we have to proceed with what? We have to proceed with really raising powers first, raising each one of these to the power 7, power 4, and power 5 respectively, once we knew the values for x, y, and z, because exponents comes first. And then once we're done raising exponents, so if we were doing, as I said, if we were doing a calculation, a plain old calculation problem, exponents comes first. Well, and I said first simply because it's inside the parentheses here, there are only two operations, raising powers and taking products. So, of course, among the two, then raising powers comes before multiplication. So that one comes first in the two here. And then after that, we're going to do the multiplication. So that's for a simple calculation problem. But now think about the work that we're going back. Think about this work where we're breaking it down. This work where we're breaking it down from one single log to multiple single log terms. We reverse the order. We reverse the order. So when it comes to this, take this as a note for anyone, in case no one explained this to you before. Okay, think about we reverse PEMDAS. Okay, when we're making our attempt to break a one single logarithm into multiple terms, then think about we reverse PEMDAS. That's why. So now, if it was a calculation and we have to do powers or exponents before multiplication, then now when we're breaking it down, then we have to tackle down right to these products first. We have to apply the rules that applicable to these multiplication before we use the rules that handles the powers. That's why I said reverse PEMDAS. And that's the reason why back in my steps, the reason I did this first, turning the logarithm the way I see it, I see the products that caught my attention first. Okay, and so I use a rule of log that turns a product or a quotient into sums or subtraction. So that has to be done before using some rule to handle the power. And that's why it explains that the step here where I broke it down to multiple terms comes before the steps where I brought the power down and turned them into coefficients in front of each term. That's why. So think about we're reversing PEMDAS. Okay, think about we're reversing PEMDAS. And so now once you've caught that, I spent a lot of time explaining that idea of how I did that right in example 3 part A. And now once we've caught that, and this is my biggest advice right here for anyone, okay, when we're doing this kind of problem, think about we reverse PEMDAS. Once we take that, and of course it's not always easy to do that. It's easy to say through the mouth, but it's not always easy to do that. And that's why there are the more problems I'm going to put in the example. But at least now I have a guidance so that you can see how I stay consistent within myself for the later problems. And it also will minimize my amount of time explaining through every step. Okay? All right, so now let's head out for the next problem in the same example. All right. This may seem a little scary, okay? But let me now call that part B of the example, and I'll produce the following. How about log base 10 of an x, how about brackets right here, log base 10 of an x squared times a y to the 5th, okay, and then raised to a 10th power. Okay, x squared, the product of x squared y 5th, but then in parentheses to a 10th power, and then we take log outside of that. Okay, and now see, clearly speaking, the problem starts out with only one single logarithm term. But how are we going to break that down to expand that into multiple terms similar to the earlier problem that we did? Okay, so here's anyone already heard my advice earlier. So now allow me to directly apply that advice of mine into the problem right here. So again, think about reversing pandas. If we were using pandas to do a simple plain old calculation, then we have to start from the inside out. And we have to start out with the following. See? Pandas stand for parentheses first, and then the exponents, and then multiplication or division, and then adding or subtracting. Okay, so now of course we're working with the part, we're thinking about the part inside of the log, but then inside of the log there's a parentheses. Okay, so according to the order, and we have this has to be the higher order compared to that power right there. Okay, so this inside right here is higher power, is higher priority than that number 10, but then inside of the parentheses here, okay, there's even, and then when we already got inside of that, then the raising these powers right here is even higher priority than the multiplication there. That's how I see it. So really, if I was doing the work right here, then raising the x to power 2 and at the same time raising the y to the power 5 is the first thing to do. And then the next step is to multiply the 2. So product comes step 2. And then after that product, we raise that to the 10th power. That's step 3. So the raise to the 10th power here is the last step before the logarithm. So if that's how I apply pandas if I was doing a plain old calculation. So now if we are thinking of that and start thinking about reversing pandas, reversing pandas to break down this logarithm, then the 10 here have to be handled fast, because the 10th here is an overall power. So, and it was the last one, it was the third operation to be done if we were doing it was the last one before the logarithm. It was the last one to be done, okay, for the inside of the log right here. So in that way, now I'm going to immediately apply rule number 6. I'm applying rule number 6 here is going to bring it down to, so now it's going to bring it down to rule number 6, apply it in and bring it down to a coefficient 10 times log base 10 of this product, x squared times a y to the 5th. All right, and now aside from that coefficient 10, the log of each one of these, and you can see that it's now very similar to the earlier example that we've had already. Okay, so now the 10 here, now keep in mind the 10 is playing in the role of a coefficient, meaning it's multiplied with that. And so now I'm going to keep the 10 here, but in the next step, see, now I'm about to apply rule number 4, property number 4, to break this product, because now in that product, again, reversing the pandas, then between these two, exponents comes before the multiplication if we were doing a plain old calculation problem. So now reversing pandas, then we have to apply a rule that breaks down the product here, the multiplication here fast. Okay, and so in that way, now it becomes that's the reason why we have 10 and multiply with now a parentheses here. And then this giant space here is ready for two terms. Log base 10 of x squared plus log base 10 of y to the 5th. That's how I see it. Now at least I have two terms. And now the 10 here is a common factor for each one of these two terms. Because see, it was the whole coefficient 10 multiplied with the entire thing here. And then just aside from that 10, just the log itself has got broken into two separate terms. It's got turned into two separate terms. And so the 10 here has to be, needless to say, to explain, it has to be a common factor for both of these. Okay, so now we can distribute the 10 in there. So that's making it 10 logarithm base 10 of x to the square plus 10 times logarithm base 10 of y to the 5th power. Okay, and then now at this point I clearly have two terms. Each term already has a coefficient 10 as a common factor, but then we're going to apply rule number 6 one more time. See, we already applied rule number 6 earlier, and now we apply rule number 6 one more time. Okay, and so I'm not saying that my solution is the fastest solution, but at least it lays down that step-by-step foundation right there, and it stays with that advice I've had earlier for anyone. it's the easiest route, even though it's a little easiest to understand route, but even though it may be a little longer. Okay, and then now rule number 6 applies again. I'm going to bring the power here inside the log in front, multiply, combine together with this factor in front. It's now going to become a 20, but now log base 10 of just x power 1. All right, plus, and then that 5 right here can be brought down using rule number 6 that we've learned, property number 6 that we've learned, and then multiply, combine with 10 together with 10. I'm looking at plus a 50. Okay, log base 10 of y. And that's how I'm done with my problem in part B of the example 3. All right, that's how it's done. So think about reversing pandas when we're doing this work, expanding from one single logarithm to multiple terms. All right, let's keep trying a few more. Let's keep working through a few more problems right here. All right, so now I'm ready for part C of the example. All right, so what about we are looking at, so log base 10, okay, or how about let's switch to ln right here, okay, just change out, taste a little bit. Okay, so natural log, different log, but it works the same properties will come out. Natural log of a to the 15, b to the 13, so it's a product in the numerator, and then we have a over c to the 17. All right, a to the 15 times b to the 13, and all over c to the 17. Okay, all right, so things are starting to have a lot involved here, and so that even if we already had that advice about reversing pandas, okay, how are we going to handle that? Okay, so now we're going to just need to sit down a little bit, or sit back a little bit and think a little more thoroughly. See, if, like I said, always put yourself in that situation. If I would be doing, or if you would be doing a plain old calculation, or just punch. Now, of course, we only focus on the part inside of the log. So if you would proceed into calculating the expression inside the log on a calculator, this is where bringing up a calculator is the best example over here. If we were typing this in a calculator, what is the order of operation for the calculator to understand and get us the correct result? Okay, so this is how I see it. Right, so yes, I'm trying to explain how I can reverse pandas in this problem, but it's starting to get even a lot more involved here. And there's multiplication and division. By the way, let me finish writing it down. A to the 15, b to the 13, but over. You see, and when I was writing it, I wrote that product first before the division. Over c to the 17, okay, and inside of the whole quotient is inside the logarithm. So back to what I was saying when I was standing on the other board. If we were doing a plain old calculation of the expression inside of this logarithm on a calculator, and how would we make the calculator, or how would we type that as a command, as a syntax in a calculator? Okay, so this advice is already good enough, stays there for long enough, so let's erase that away. So here's the thing. If we're typing this to reflect order of operations, to reflect pandas into a calculator, then it needs to be as following. In parentheses, a raised to the 15 power times b raised to the 13 power. And really, anyone is going to understand that among these, and raising power comes before the multiplication. But when we're really typing this into the calculator, we understand that all that here as one parentheses operation. So we have to take care of all of that here first into parentheses, and we divide. and then we open another parentheses. So imagine if we were typing this in a calculator, that's how we would type it. Okay, and then c to the 17. Okay, and so that's why parentheses, exponents, and then multiplication or division, and then last one is adding or subtracting, addition or subtraction. And so now according to this way how I wrote it down, see, this is done, has to be done inside. So there's a division here, but whatever on each of these has to come before the division here. The part I underline, each one of these has to come before the division. That's how, so we already start seeing the order here. This one here comes, the division comes after this product, and after that raising power here. All right, and then for each one of these components, so now that one inside here we have what, the product, and then raising powers, and then product. So that means this one here really allowed me to write it in red ink right here. Raising power for the calculator, raising the two powers here is the first priority, and then this one right here is number 2. Okay, and then at the same time the calculator is strong enough to do these two, so it's also going to be first power, right, or first level right there. And then but step 2 is here, and then step 3 is to take care, this one right here is the last one. All right, so now in that way, when we are reversing PEMDAS, so I wrote down with these red one right here to explain that if we were using PEMDAS for calculating, then first we have to raise power on each one of these. Once we know the value of A and value of B and value of C, we raise power of these. Okay, and then we multiply. That's step 2, and then we're gonna put a dividing. All right, and so now in that way, according to that operation, and now reversing PEMDAS, then here we have to apply a rule that breaks down this division, because this division, according to PEMDAS, this division happens last. Okay, and so now reversing that PEMDAS right here, then we're looking at I'm going to apply rule number 5 right here to break that down into a logarithm natural log of a to the 15 times b to the 13. But now I'm going to subtract a logarithm natural log of c to the 17. That's how I'm doing it. Okay, and then see, so now in my next step, the last term here is simply just having a power, so we can save it there, we can hold on to that and make it the same step with the later, but right now it's a product, and now it's easy to reverse the PEMDAS here among these two, the little factors inside of my logarithm. So in my next step I produce the following. I apply rule number 4 right here and turn that into a logarithm natural log of a to the 15 plus the natural log of b to the 13. And then don't forget, we still have that final term minus natural log of c to the 17. All right. And then now each one of these is simply just one single logarithm, and it has a power inside a log here. Now we can just apply property number 6 to bring the power in front and turn that into a coefficient. All right. And so now continuing my step here, then in my next step I would end up with 15 natural log of a. And now I know that I'm done for that first term, because now inside of my logarithm, whatever base that is, I have just simply a power 1 of that value. Plus, now in my next term is a 13 as a coefficient, multiply with natural log of b. And again, I know I'm done for this middle term right here, because the number here is just raised to power 1. Okay, and then now minus, and here I'm looking at 17 being brought in front as a coefficient, natural log of c. Now I know that I'm done. I have completely expanded my logarithm from the beginning. From the beginning, it was a logarithm of a quotient, and then each part of the quotient individually has a lot going on right there. All right, and so that's how it's working here. Okay, so from one single logarithm, I turn it down into 3 separate terms step by step, and then at the last step we took care of the power, because the power here, when we were doing it, it was the very first step, and so now, you know, when we're breaking it down, expanding a logarithm, it has to be the last step to take care of. All right, and so that's how I reversed PEMDAS in this particular problem in part C of our example 3. Let's continue. All right, so now let's look at part D of our example here. So how about we're looking at natural log of, and here I'm looking at how about a square b cubed, and then there's a c to the 5th, and then d to the 8th, okay? And now this is even making it more clear about how we reverse the PEMDAS right here. Okay, and so now this problem here has a little more involved than part C we've done earlier, but the idea, the foundation is exactly the same. Okay, the reasoning is exactly the same. So the quotient here looks like, and that is a square, so a squared times b cubed, whatever that is, divided by c to the 5th times the d to the 8th, like that. So these two parts comes before putting them into a quotient. Okay, and so that's why now when we are reversing the PEMDAS, then I'm going to use that rule number 5 to break this overall fraction into 2 separate logs. So now I have a logarithm, a natural log of a squared b cubed. Now I'm subtracting a natural log of c to the 5th in product with d to the 8th. That's how it happened so far. And then, as I said again, this is not the only way of approaching it. And for anyone who is fluent with these operations, there are other ways of handling it as well. Okay, but now I just want to explain that in a way that's easiest to understand. All right, and now on each one of these, now think about, we have 2 separate works. So for the first work, it's easy enough, just like how we've done in the earlier problem. That one here produces two other terms for us. One of them is a natural log of a squared plus natural log of b cubed. I apply property number 4 here. The log of a logarithm of a product turn into sum of 2 logarithms, okay, 2 logarithms of the same base. And I didn't have to worry about the powers yet. Now, anyone, before I get into that next one, anyone viewing the lesson should have already had something in mind. But be careful. All I'm asking is be careful. So see how I do it. Now, yes, if you had that idea in mind of using the rule number 4 again here, I agree totally. I agree totally. But be careful. There's a subtraction here. So now I say keep the subtraction, and then I have to open brackets. I have to open brackets. And now opening brackets, leaving us some space to only handle, because parentheses or brackets indicates a sense about isolating, okay, a sense about isolation or grouping. So now I want to group things aside from the subtraction sign right here. So just produce another group. So now that group about to fill in here comes from the logarithm of this product. So now inside of the brackets I can have a logarithm, a natural log of c to the 5th plus the natural log of d to the 8th. All right. And now we're going to have to remove the brackets here by distributing that minus sign to each term. So the minus sign distributed for each term right here. Okay. So it looks like I'm going to also need the space on my other board. All right. And so now, in my next step, things become, so first term is natural log of a squared, next term is natural log of b cubed, okay, and then I'm going to have a minus natural log of c to the 5th minus natural log of d to the 8th. And now I can just simply apply that property number 6 to bring the power in front the power in front as coefficient, bring the power here in front as coefficient, and bring that power here in front as a coefficient. Okay, and so now in my last step right here, I'm going to have 2 natural log of a, and now I'm really convinced to myself that I'm done with this first term because there's a coefficient, there's a log, and then inside the log is power 1. All right, plus, and now it's 3, it's natural log of b. And again, now I have a high sense that this is ending point for my problem right here. Have a coefficient, okay, and it's just power 1 inside a logarithm, regardless of whatever base that is. And now minus 5 natural log of c, and then minus 8 times the natural log of d. All right, and now I've expanded my logarithm from one single log term to multiple log terms. All right, and again, this is not the only way of approaching it. That's not the only way. At least it's one style of mine that I made clear. My philosophy of these problems is that we are reversing parameters, okay, step by step. Okay, but then along the way of that we're reversing parameters, when we're breaking it down, people can still approach things differently. Okay, so go ahead and experiment things out. All right. But I still didn't plan to finish with example 3 here. Let's do about a couple more problems in example 3. And this skill is extremely important. The reason I really focus, because again, this class that we're taking is called a pre-calculus class. This skill will be emphasized, will be used actually. This skills, once emphasized here and learned thoroughly here, this skills will be used very intensively when you have arrived at your calculus course. Okay? And so that day will come for anyone who's planning to take the calculus immediately after this class, or in some future decide again to take a calculus class. And so this is the reason why I would like to really focus on this skills, really emphasize on this skills, because I've seen a lot of my calculus students still going a little loose with this particular skills when they are doing my work at the calculus class right there. Okay, and so now let's look at part D of the example. Part E of the example. So now how about let's switch back. I'm using a log base 10 right here. Now I'm having a square root, okay, of, and then inside the square root, x to the negative 3, y to the 4th. All right. Log base 10 of square root of x to the negative 3, y to the 4th. So we got a product inside the square root, and then the product of two separate powers, the product of two powers. Okay, so to make it clear with the parameters right here, allow me to rewrite, rewrite the expression to make it clear with where the parameter is and all that. So I'm going to rewrite the problem as a logarithm of, and now you see that x to the negative 3 in product with y to the 4th. All of that there, I see that as being inside of a 1/2 power. Being inside of the 1/2 power. So now clearly I see parameters. See, if we were doing a plain old calculation on the calculator, we would have to raise each one of these to a powers first. And that's how a calculator would do it as well. Okay, raise that to a power negative 3, raise the y to a power 4. And then take product is the next step, or in here is step 2 so far. And then in parentheses, after parentheses, we're going to raise to the power. Okay, we're going to raise that to the power 1/2. And so now we're going to reverse the parameters. Okay, we're going to reverse the parameters. So that means I'm going to use a rule that take care of the things that outside of the parentheses is first. Okay, so in that way, here's how I'm seeing it. Now, if we're reversing the parameters, we're bringing that power here, that power 1/2 down first. And so now it brings it back to that problem similar to part B that we were doing earlier. Now we have 1/2 multiplied with log base 10 of a product x to the negative 3 times y to the 4th power. All right, and now in here among the operations that we have multiplication and raising powers, then multiplication comes before raising powers. I mean, we have raising power comes before multiplication. So now we have to break it down. We have to break it down according to the multiplication before we breaking down the powers. That's what I meant earlier. Okay, so now I'm gonna, and so now at this point it's very similar to that problem we've done in part B right here. I'm writing this as a 1/2, okay, and then I produce a pair of brackets right here, and now I have log base 10 of x to the minus 3 power plus log base 10 of x, of y to the 4th power. Okay, so that I had that sum right here due to breaking down that product right there. I used rule number 4 on that, aside from that coefficient 1/2. And that's why I kept that 1/2 as a common factor here outside of my brackets. All right, and then in the next step, we're just gonna distribute that 1/2 for each term here. So that's making it 1/2 log of x to the negative 3 plus a 1/2 log base 10 of y to the 4th. Okay, y to the 4th. And now we're going to apply property number 6 to bring the powers in front. Okay, so now I'm going to bring the power in front and multiply together with the coefficient already existing there in front of each of our term. Okay. So now in my next step, here's how it happens. Okay, so the first term becomes a minus 3/2 log base 10 of x. And I have a high sense that now I'm done with that first term because we have a coefficient, negative coefficient. It's okay, but coefficient with log, and inside the log we have a power 1. Okay, and now plus, and then 4 multiplied with a 1/2 is now just a 2. Okay, so log base 10 of y, and then this is our final expanded expression after we have expanded from one single logarithm term to multiple log terms like that. All right. All right, so in that way, let's now look at the last one of our example 3 right here. So problem F right here. So how about log base 10 again? Okay, even though it works, it's the way we're doing it, it's the same for any other log of other bases. Okay, so log base 10, how about I have x cubed y squared and then multiply with in product with a square root of x to the 5th times y to the 7th inside the root. Okay. All right, and so it has a lot involved here. But then once again, stay with my advisor here, reverse PAMDAS. Okay, and so we have product, and then there's a product with a square root, and then inside square root there's something. So according to PAMDAS, then these calculations inside has to be done before taking square root. And then another way, the extra information, just like the earlier problem I've explained, think of that square root as an overall power 1/2. So how about one step to rewrite the expression? Logarithm of x, log base 10 of x cubed in product with x squared in product with a, so how about I keep this as brackets, x to the 5th, y to the 7th to the 1/2 power. Okay, so let's keep things like that. Okay, so now clearly with the order of operations, see, we have to take care of those inside the parentheses first, because this is one group, and then once we're done with that group, and then that group as one is being at the same order, okay, at the same precedency with these two other inner products. So this product, we have a product of 3 factors, but then inside of that factor we have a product inside of that parentheses. So the whole parentheses here with a power is one factor of a bigger product. All right, so now reversing the PAMDAS right here, then this product right here has to be the last one after being the part inside here. And so now in that way, I'm going to break it down as following. I have a log base 10 of x cubed, and there's a product here. So these products are at the same level of priority, plus log base 10 of y squared plus a log base 10 of that x to the 5th, y to the 7th, to the 1/2 power. All right. So that's how I reverse my parameters for the first step like that. Okay. And then for the next few steps, I'm going to hold on to these. We can even break that further down like that. And so now that works just like that example problem I brought in earlier. So now on this board space of mine right here, I'm going to keep the first two terms the same. So now log x cubed plus log of y squared. Now I'm going to add. So now I have a 1/2 multiplied with log of a product of x to the 5th times y to the 7th. Okay. So just that, and this order of mine is not the only order. Some other order can also work. But now I've that power 1/2 from the earlier step of this last term right here, I brought it down in front as a coefficient. Okay, and now in my next step, I'm still going to hold on to the first two because they're quite simple. Only one more step that take care of the first two terms. So I decide to keep it there. Okay, for now to hold on to it. So log base 10 of x cubed plus log base 10 of y squared plus, now I keep a 1/2 as one common factor. Okay, and now I'm going to break that similar to the earlier problem. I'm going to break this product into a log base 10 of x to the 5th plus a log base 10 of y to the 7th. All right, and now I'm going to do the following. I'm going to distribute that 1/2. So that's leaving it for me. That's giving me log base 10 of, well, the x cubed, these two first terms are still being kept the same. Okay, but I have a 1/2 log base 10 of x to the 5th plus a 1/2 of log base 10 of y to the 7th. All right, and now I'm going to apply property number 6. Because all of these now is just simply a log with a power, log of a number with a power, log of a number with a power. These two have some coefficients, but then at least these are all at the same level now. Okay, and so now in my first term here, it becomes a 3 log base 10 of x, and now I know I'm done with that first term. The next term here is 2 log base 10 of y, and now I know I'm done with that next term right there. All right. And then now for the third term here, I'm going to multiply the 5 in the front together with the 1/2. So I'm looking at 5/2 log of log base 10 of x. Okay, and plus, now I'm looking at 7 multiplying down together with 1/2. Here is going to be a 7/2. Okay, log base 10 of y. Okay, so as far as breaking it down, we know that we're done to each one of these terms. But let's not just simply stop here because we can realize some further things. We have like terms. For example, these two that I underlined in red, they are like terms. And these two that I underlined with a little red cross like that, they are like terms. They're like terms in the sense that they have the same log base 10 of y. These are like terms because they have log base 10 of x. Okay, so now we can combine like terms. So combining like terms at this case is just simply we adding the coefficient. Okay, so for the log base 10 of x, we're looking at, after combining like terms, we're looking at 11 halves log base 10 of x. That's after adding 3 and 5/2. Okay, so 11/2 times log base 10 of x. I'm going to add with, and the next one here, log base 10 of y, 2 log base 10 of y plus 7/2 log base 10 of y. Okay, So I'm looking at another 11 halves, okay, log base 10 of y. And this is where I would say I'm done right here. All right, that's my final answer right there. All right, and again, I'm not saying that this is the fastest way, but it breaks it down in a way that it's easiest to understand. And then for anyone learning from this lesson right here, you can also rely on your own skills, your own background in math, in doing all of the algebra work, and you can have an approach that's shorter than me, okay? But that requires some more advanced experience. So I'm showing this approach here for anyone learning in this lesson with the minimal experience in math right there, that can still follow through right there. Okay, and then as you build your experience, you're going to start developing your own efficiency, your own method to reach better efficiency. Okay, so that's all we have for example 3. And again, as I've said, no instructor would be able to include all kinds of problems out there for any kind of examples. Okay, so allow me to finish with example 3 here and call it an end for example 3 here. And move on to the rest of the lecture. And then if you are learning directly with me, at some point there will be a way for me to directly contact me so that I can clarify extra understanding when you run into an assignment that has problems that a little bit aside from these problems I cover here. Okay. All right, and then now we are looking at the two last properties of among our properties of the logarithms here, and these are, of course, they are proven too, but I would consider them as some special properties right there. They're also proven, some properties that require some math to prove them, but then I regard to them as special properties. Okay, so special property. All right, some other special properties right here. So we've learned from the easy properties in the beginning of our lecture, and then we moved on to the proven properties, the number 4, number 5, and number 6. And now we're going to look at 7 and 8, and that completes our list of all the properties with logarithm, with any logarithm. So I'm going to directly write down the rule over here. Okay, so when it comes to logarithm, we have the following. It's a little hard to see, but it will work out. Okay, how about see, x equals x here represent any number. But of course, well, I shouldn't say any number. Any number is a little too much to say. X is a positive number. For any positive number right here, then we can express x here as a raised to the power of log base a of x here. Things looks a little strange. See, it's a shock to see. No one out of nowhere can think of this, but it's a known rule. So now it doesn't have too much of a direct application. That's why I saved that as the last, so that I can just talk about it at the minimal amount of discussion about it. Okay, and then you will see that maybe once or twice in your later future courses. It doesn't have too many applications out there, but it is a real existing property of logarithm, and it deserves some attention on it. Okay, so any number, as long as the number is positive, any positive number can be written as a base a raised to a log base a of x. And so of course in that way the base a also has to be a base where it's positive base, okay, positive base and other than 1. It's a base of a logarithm, so we got to make sure that it meets all of the requirements of a logarithm to be the base of a logarithm. Okay, but so let's find out why it's like that. Okay. Well, as a quick demonstration, just think about okay, 5 is a number itself, positive. So I can always rewrite 5 as and pick a base. And I mean, right now in my own creativity, I'm thinking of 3. So 5 equals 3 to the log base 3 of 5. That's what it is. Okay, like I said, so it's doing something like this it's not very useful. It's not really showing anyone anything. You will see some better applications about once or twice in your time learning about calculus, or in some of the future courses. But I just want to point out why it's true. This is not really why it's true. This is just an example that So now from this understanding any number, and we pick another number, as long as it's positive and other than 1, then we can have that 5 equals 3 to the log base 3 of 5. I picked that number. So the same here, you can think of 5 equals base e of natural log of 5. Okay, but where it would be a good place to see a good usefulness of this, wait for a higher course. The closest one is calculus, but again, it's only once or twice you're going to see the application of this, but it's worth it to mention sometimes. Okay, so let me now quickly explain how the mathematicians, the generations of mathematicians before us came up with this. How did they out of nowhere come up with something like this? It looks really crazy, and when I was a student myself, I was shocked too to see this, and it took me that many years until now in these days to become fluent with that. Okay, so don't worry if it's a shock to you at first, and if it's a little hard to use at first. Okay, so here's how I'm seeing it. Don't we always agree? Don't we always agree that a log base a of any number, I mean, of course, if x is meeting with the requirements of being the arguments of a logarithm, and then base here is a value that meets the requirement for being a base, then we have to agree to ourselves that log base a of x is always equal to log base a of x itself. Like, this is needless to say. Okay, any quantity equals itself. Okay, and now we've learned from our understanding. See, if things are plain old like this, then it's easy to recognize. Log base a of x equals a y, then we have what's so-called the exponential form of this. An exponential, this is a logarithmic form. So if we connect back to what we've learned from the introduction lecture right here, then this is called, this is an equation in logarithmic form, and we have an equivalent equation in exponential form. So in exponential form, it's a, base a, but raised to the y power to equal x. Anyone must agree with me on this. After we have seen that or have watched that lecture on the introduction of logarithms prior to this particular lecture here. How do I see that in here? Well, if I think about, if I take one side, of course, log base a of x, gosh, it has to equal log base a of x. I mean, it's doubtless about it, no doubt about it. Okay, but now let's just fix this. Let's just fix this as one crazy y like that. Okay, let's fix that with one crazy y variable. So if I substitute that, when I said fixed earlier, I meant if we assign that whole one side right here, if we pick one side, because they're the same. So if we just simply pick one side and assign that to a crazy variable, capital Y, for example, then we produce the following. Log base a of x equals y. And now the story is slowly becoming clear. This is an equation, the log base a of x to equal some crazy variable y, but it's an equation in logarithmic form. And now we will have that, and now at this point here, it would be easier for anyone to turn this into the exponential form of the same equation. So now exponential form we're looking at, so in exponential form we're looking at base a raised to the power y, that's crazy variable, to equal x. Base a raised to the power y to equals x. But hey, wait a minute. What was y? We decided that y is this crazy variable y is 2 equals all that log base a of x. So that means, isn't that we can substitute that expression back for y in here, for that crazy crap capital Y. So our another version of this comes straight out is that we ending up with a raised to the log base a of x to equals x. And ladies and gentlemen, that's how I have just proven this result right here. Any number x can equal a raised to the log base a of x. All right, but so it's proven, but again, at this level of our learning right here, I'm not able to show too much applications of that. Literally speaking, none. But there will be a few occasions where you will have to use this property when you arrive at your calculus course, where quite a few instructors use this to prove a few rules at the calculus courses. So that's why it's really, and the course we're learning here is a pre-calculus course. So be patient with whatever I'm teaching here. It's a thing that's prepping you for the later courses. Our course is entirely aiming at for any one of you to move on to a calculus course and to be successful there. Okay, because you have seen all of this at least once or twice, and then so that you won't be shocked when your instructor there at the higher courses bring it out. All right, so that's property number 8. Okay, so I'm gonna quickly erase that, and then show the next one. Or indeed, actually, I'm gonna use the other board space right there. All right, so I have left this work here long enough. So let's now look at property number 8, and that completes our list of all the properties of logarithm. All right, so ladies and gentlemen, I still remember clearly that when I was recording that lecture where I introduced about logarithms, in order to show you how we ran on how we operate with the calculator, a log as following. Say, for example, log base 2 of 5, for example. Okay, the calculator, the biggest problem is on the calculator. There's no direct buttons for log base 2. The calculator, any calculator, even the most advanced one only has the natural log, admittedly, and a log base 10. That's the most the calculator offers. Other than that, more basic ones only have either one of these. So the trick I did there on the calculator, on any calculator to do this, I was doing the following trick, and I already introduced this to you that early. What I did, we can make a choice. We can make a choice, and I yelled it out loud in front of the camera in that lecture there, that we can make a choice between going with a natural log or a log base 10. So this same work calculating log base 2 of 5, we can do on the calculator. Somebody can do natural log of 5 divided by natural log of 2. This is log base e of 5 divided by log base e of 2. Or someone can also, it's a different choice. Either way, it's going to land us into the same exact answer. Log base 10 of 5 over log base 10 of 2. We did this, and we got the exact same answer, and that showed us how we can get to the actual answer of log base 2, a general logarithm here. And I remember clearly that I yelled out loud in front of the camera with the lecturer there that I owe anyone viewing the lesson there a big explanation of why it was done that way. Now it's the right time to unlock that explanation right there, to unlock that little secret I've been holding the whole time. Okay. So, this last property I'm about to introduce right here, property number 8, ladies and gentlemen. So, now for any general log, and we have to, so log base a of a number b. Log base a of a number b. Okay? Can always be done. Log base a of a number b. Of course, a here is a number that is a value that meets with all the requirements to be the base, so needless to mention that. this b right here is a number that's being the arguments of a logarithm, so it must be a positive value. Needless to mention about that. Okay. So now this log base a of a number b will always equal to. It's a proven rule, special enough in a way that I have to leave it at the last one right here. It will be the same as log base c. We were working with log base a, but now all of a sudden we just switch to log base c. Yes, and that's the idea. C is just any chosen rules, any chosen base other than a right there. Log base c will always equal to log base c of b. The number inside the log here first, and then dividing that by log base c again of a. All right, so it will always, and then here for any c value being positive and other than 1. Any c value positive and other than 1. We can also use c to be exactly the same as a too, but it's not getting us anywhere. So the most direct application of this, the most direct usefulness of this is where we saw it earlier. See, if we were doing this on a calculator, log base 2 of 5, the major problem here is that any calculator, no calculator on this in these modern days has a button for for log base 2. No calculator has a button like that, because I may have made it this to seem like a joke, but if the engineer who created the calculator made a button for log base 2, then immediately log base 3 is going to complain. How come you are so unfair? You made a button for him but not for me. Okay? So any engineer designing a calculator has only decided, hey, it's a firm rule. We're only doing that for natural log or a log base 10. Okay? Because those are the two that internationally used and widely used enough internationally. Okay? So log base 2, log base 3, log base 5, let's leave them all out. Okay? Because there's a way to calculate them. You see, so on the calculator, the reason I was able to choose, see, I was doing this, ln of 5 and ln of 2. See, the truth behind the scene with this is that ln of 5, we learned that it's a log base e of 5, and then log base e of 2 going in the denominator. So this is playing in the role of that c right here. So we start out with a base 2, and then we have our right to always change that. Using this formula, we have our right to change that into a different base, as long as the different base we choose here is useful for us. Okay, and so on the calculator, we purposely chose base e, and so now it's log base e of 5 of the big number divided by log base e of 2, the base number, and then this will get us the actual answer of log base 2 of 5. Okay, and that's for that same reason I was saying out loud when I was introducing that. Somebody else can also choose, can go with the route log base 10 of 5 over log base 10 of 2. See, I was saying that clearly, log base 10. So we can also choose a base 10 right here, 5. For some rare instance right here, allow me to write the base of base 10 of log base 10 to demonstrate the idea. But see, this is some base that we chose, purposely chosen, so that it's different with the original base, but it helps, it gives a good purpose, it becomes a good purpose, it helps the calculation. Okay, so the c here now at this point is just any chosen c. Okay, any chosen base, as long as it meets the requirement to be the base. It can also be the same as the beginning base as well, but it's not getting us anywhere. So this rule here is, some textbook, and some textbook mention the name and some textbook doesn't. Okay, but for anyone learning with me here, allow me to just quickly, briefly mention the name here. But This rule is called the change of base. Okay, change of base rule. The rule that allows us to change the base from, see, we change from logarithm base A of a B, and then we change that into an entirely brand new problem, log base C of B. We change to a completely different base. We have our right of doing that. All right, but we have to change under this rule over here. All right, the rule to change base. But then why is this useful? It's useful for us to, when we're in that situation that we have to enter a general logarithm calculation into any standard calculator. It doesn't even have to be the TI-83 or 84 that we mostly use for learning purposes. All right. So that's all I have for this lecture about the properties of logarithm for here. Okay.